Hi, in today's video, we're going to be talking about the last section of this semester, reduction and oxidation. So in this video, we're going to talk about the general concepts of oxidation and reduction, and I'll also go through all of the reagents that we're going to see throughout the rest of the semester. And then there'll be follow-up videos for each of these reagents and show you specifically how they work and how you would use them in synthesis. But today's video is kind of a big overall overview. So if you have a molecule like an alkyne, you can reduce that molecule. And so reduction is, you can think about it as formally adding an equivalent of hydrogen gas, H2, across a triple bond or a double bond to now do one reduction. Sometimes we abbreviate this with a bracketed H. We can reduce the alkene further to an alkane. So an alkene has a higher oxidation state. It can be reduced to an alkane. And again, we use this H bracket. And again, I can say we've formally added an equivalent of H2. This reductions can also occur from oxygen-containing compounds like carbonyls. So if we look at a carbonyl like this, and the book often has carboxylic acids, but really it applies to acid chlorides with a chlorine here, to esters where there is an OR group here, and also to amides. But again, the book will largely focus on carboxylic acids. You can reduce a carboxylic acid by effectively adding H2 across that bond, and that will give you an aldehyde from that carboxylic acid. You'll note that you also end up with the equivalent of HX, where that X could be an OH, so you'd wind up with an equivalent of water in the case of a carboxylic acid. And so that's where the second hydrogen is going here. You can now further reduce an aldehyde to an alcohol, and again, we can use that bracketed H as our a quick designation of reduction. So an acid gets reduced to an aldehyde, which can get reduced to an alcohol. And on the opposite side of things, the alcohol can get oxidized to the aldehyde. The aldehyde can get oxidized to the carboxylic acid. So we call that those oxidation steps, and we use this bracketed O to denote oxidation. So now let's look at some of the reagents for reduction first. So if you have an alkene, a common reagent that we'll use to add hydrogen gas, in this case truly hydrogen gas, is palladium on carbon. So this is a heterogeneous catalyst. That means it's a solid supported catalyst. And what happens is you add this H and H across the double bond, which now gives you an alkane. If you start with an alkyne instead, you reduce to the alkene, but you can't stop there. It reduces all the way to the alkane. So alkynes get all the way reduced to the alkane if you treat it with palladium on carbon. I'm going to highlight that if you now had an internal alkyne instead of a terminal, you'll note that you wind up with a cis bond formation. So you end up with the two hydrogen atoms being added across the same side of the molecule. That's also true for an alkene to an alkane, but we don't see evidence of that for this alkane because there's free bond rotation. Now there's a special catalyst called Lindlar's catalyst, which is kind of an interesting mixture of molecules, also solid supported, also with palladium, that will give you the cis alkene from the alkyne, and it will stop there. And that's because the catalyst is poisoned. We'll talk about that a bit later. But let's say you don't want the cis alkene, but instead you want a trans alkene. You have to use a different set of reagents. You use metallic sodium, so this is just a chunk of sodium, in liquid ammonia, and this will give you the trans alkene, and the hydrogen atoms come, in this case, from the ammonia. Now, when we are trying to reduce compounds that have oxygen atoms, we often use hydride, H-, as our source of reductant. And we have to use our hydride with special reagents like lithium aluminum hydride. It's a really potent reagent. Lithium aluminum hydride will take an epoxide and it will reduce the epoxide to an alcohol. So it will break one of the carbon-oxygen bonds. And it does so in the same manner as a strong nucleophile would react with the epoxide, so it goes at the least hindered site. So again, if I highlight these hydrogen atoms here, one of the new carbon-hydrogen bonds came from the lithium aluminum hydride. Another time where you'll see lithium and aluminum hydride being used is when you're reducing a ketone to an alcohol. So in this case, again, the H of the hydride winds up bound to the carbon where there was a carbon-oxygen bond. And I'll point out that both of these steps have a workup step, and that's actually where these extra hydrogen atoms come. If you were working through the mechanism, you'd find that there would be a pendant oxygen with a negative charge. So we add a workup step to give that extra proton to each of these steps. I'll also point out that aldehydes can also react similar to ketones to give you alcohols, but in that case, there would be a primary alcohol, so the oxygen would be at the end of the carbon chain. There are some other oxidation reactions we're going to talk about in this chapter, and if you have an alkene, you can oxidize that in one step to an epoxide using a reagent called MCPBA, and we'll see how that works in a following video. If instead of trying to make an epoxide, you want to just oxidize by making carbon-oxygen bonds, you can also do that. So using osmium tetroxide and also with NMO, we'll see why we use that, it makes it a little less toxic, you can get these diols. Note that this diol is a syn diol, so these two alcohols are on the same side of the molecule. If we were to treat this epoxide with sodium hydroxide, that would crack open the epoxide, but you'd wind up with a trans diol. So if you want a trans diol, you make an epoxide and you open it with sodium hydroxide. If you want a syn diol, so on the same side, you use osmium tetroxide. Another type of reaction that we'll see with alkenes is we can do ozonolysis reaction. So this is the same ozone that we talk about in the atmosphere, ozone, and then you follow it up with zinc or another reducing agent, gives you, it will break a double bond, an alkene, into its corresponding aldehydes or ketones. So if I highlighted that there's this hydrogen atom here, this gives you an aldehyde. So if you have an alkene that has a carbon and a hydrogen bound to it, you wind up with an aldehyde. If that alkene has two carbons bound to it, you wind up with a ketone. The way you can think about ozone working is it kind of cracks the alkene right down the middle, and we'll see how that works as well. Finally, you can also oxidize alcohols with a series of reagents. These reagents are relatively toxic, but these are ones that we'll talk about in the book. In modern organic chemistry, we have lots of other ways of doing this, but this is just a representative example. So PCC, or pyridinium chlorochromate, so it's a chromium reagent, that's why it's quite dangerous, can oxidize an alcohol to an aldehyde. And again, if you're keeping track of your hydrogen atoms, we've removed one of the carbon-hydrogen bonds, and we've formed now a double bond between the carbon and the oxygen. You can also use the much stronger reagent, chromium trioxide, in the presence of sulfuric acid, and this will give you a carboxylic acid, so it oxidizes all the way from a primary alcohol to a carboxylic acid. Thank you for your time, and I look forward to seeing you in all the videos that explain how these reagents work. But again, make a note cards for each of these reagents, because these are important reagents that we're going to be talking about for the rest of the semester. Thank you for your time.